Hello everyone, and welcome to another GIS lecture video. And in this lecture video, I want to build upon our discussion of sources of error by talking about a way that we can visualize these errors and the way that that plays into the geometry of the relationship between the satellites and the user in a very real way that has implications on the final accuracy of the locations that are measured. So up to this point, right, we've had this idealized concept of trilateration as being the intersection point between four or more satellites in 3D space, and that the point that they all intersected at was the location of the user. In the previous video, right, we outlined that there are some errors that can occur between that communication that can give some uncertainty to that error measurement, to that initial measurement. And so what I want you to think about is instead of having the location along the satellite, right, instead of having this distance, right, this is the distance from satellite, right, that instead of having this distance from the satellite be a single number, in reality it's a range, right, because of those errors that we talked about. And we can visualize that range by making these lines, by making additional circles, right, that are dotted. Right? So instead of being able to say with certainty that we're exactly this far away from the satellite, instead what we say is that we are within some range of distances from the satellite, bounded by this inner circle, right, and this outer circle. That we are somewhere in this distance, we're somewhere in this sort of donut, if you will, right? That we are somewhere in this donut. And so now if we take that concept and we apply that to trilateration, what ends up happening is, I'm going to try and draw this with three different colors. We'll do a white, we'll do a yellow, and then how about an orange? Right. So by our traditional definition, right, our traditional definition would have said that this location right here is the only possible location because it's where all three of them overlapped. But if we apply this concept of uncertainty, what ends up happening is we end up with these sort of bands of uncertainty around each of the satellites. So if we think about what this does in terms of positional measurements, right, what we're saying now is that, and this is going to be, I know this is there's a lot on the screen here, but let's just try and walk through this for a second. Right, that instead of being able to say with certainty that we're right here, instead what we have to say is, right, we are somewhere in the bounding rectangle where all four of the donuts overlap, which is, somewhere in this area here, right? So now instead of being able to say with certainty that we are in a single location, now we're in some area that is bounded by the errors of all of the different satellites. Okay? So let that sink in for a second, because it's kind of a leap from where we've been before, right? Before we used just a single line to represent distance, and we said that wherever those lines intersected, that's where we were. But now that we're incorporating this idea of error, right, that these satellite measurements, or the distance calculations, I should say, right, are not perfect because of all the different errors, right, we visualize that as being uncertainty. So our line, or our circular line here, becomes a donut. And we're saying that we're somewhere on the donut. And so instead of being able to have a specific point, when we apply that donut concept to all three of these, we end up with an area. We are somewhere in this area. So what I want to do is I want to go through sort of a more stylized example that highlights the issue better than my ability to draw them here. Okay, so what I've got here is I have three satellites: a red satellite, a blue satellite, and a yellow satellite. And the idea is that these dashed circles here represent the inner and outer uncertainties, right? So we know from the yellow satellite, for example, that we are somewhere between this dashed line and this dashed line away from the yellow satellite. Same thing with the blue satellite, right? This is the blue satellite, and we're somewhere between this dashed line and that dashed line from the blue satellite. And same thing with the red satellite. So what I want you to draw attention to is this idea down here that we have this green shape here. This green shape here represents that area that I was just talking about, right? So when we have these three satellites, when we're communicating with these three satellites here, given the errors that we talked about, we end up somewhere in this green area here, right? So this green area is the overlap between the uncertainties of all three of these satellites. So we've gone from, again, being able to predict a single point to being able to have to predict an area. Well, can we do better than that? Well, of course we can, right? The geometry, just simple geometry, right? That if we spread the satellites out better, so instead of having them all be clustered here relative to the user, right? The user's in this area somewhere, they're all sort of directly overhead, that instead, right, if we spread them out, that if we spread the geometry out, right, so now that instead of them all being directly overhead, right, now they're sort of one to the left, one to the right, and one ahead, right, you can see here that even though we haven't changed the error at all, right, the uncertainty is still the same, right, the distance between the inner and the outer circles haven't changed, right, that's how we visualize the idea of this uncertainty, right, but just simply by the geometry, right, by having the satellites spread out more in space, right, we're able to generate less area. So I'm gonna go back, right? When they're all directly overhead like that, right, the area that we have of potential that we could potentially be in is much larger than if we spread the satellites out a little bit, right? And so this relationship between where the satellites are and the user, this is called viewing geometry. Okay, so let's go back to our notes for a second here. Hopefully that made sense. I encourage you to pause the video, go back, rewatch that part until you get a really good understanding for how that relationship between the satellites and the user affects the area of that overlap, right? And so what we have here is, right, the relationship the geometric relationship between the user and the satellites is called viewing geometry. Right, it's called viewing geometry. And so to sort of stylize this in a slightly different way, right? If this is you as the user and you're standing here, right, with your little smartphone, right, and we have 3 satellites in space, right? If they're all sort of, you know, mostly in the same place overhead, right, and they're communicating, right, this is bad viewing geometry. Right, alternatively, right, if you go out and you are here, right, and those same satellites, instead of all being overhead, right, you have one kind of over here, you have one, you know, kind of directly above you, and then you have one maybe over here, right, and they're communicating, right, this is good or better viewing geometry. Okay, so hopefully this relationship between the locations of satellites in space in terms of their positions relative to the user, and this idea of how we visualize errors as converting a line into a donut and the point of location into this area of possibility. Hopefully this makes sense and the relationship between these parts makes sense. In the next video, what I want to do is I want to talk about what's called PDOP, or positional dilution of precision, as a way that we can actually quantify, right, this area in terms of how good or bad it's going to be on an impact to our final measurement. So hopefully this makes sense, and as always, if you have any questions, please reach out. Thank you.